Bismillahirrahmanirrahim. Dear viewers, after a long interval due to COVID-19 attack on me and after spending the recovery phase, I am again here to represent the stereochemistry course to you. Just to recall you that we were discussing about the isomerism, of which we discussed about the structural isomerism and stereoisomerism. We saw that there are two main types of stereoisomers. One of them is the conformational isomers and second one is the configurational isomers. The conformational isomers results due to the rotation of sigma bond, while in configurational isomerism there is no rotation of sigma bond. There are again two types of configurational isomerism. One of them is the geometric isomers, which is a result of a double bond which is non-rotatable. We discussed the geometric isomerism in our last session. Today our topic is the optical isomerism. The optical isomers are the isomers which differ in the optical activity. Now before we proceed further, let's see what is the optical activity. The optical activity is caused when plane polarized light is passed through a solution of chiral compound, for example S-alanine and others. The light that emerges is rotated relative to the original plane. This phenomenon is known as optical activity, and the compounds that rotate the plane of polarized light are said to be optically active. To understand the plane polarized light, at first we have to understand the nature of light. Light is actually electromagnetic radiation. It means that each photon has an electric field as well as the magnetic field associated with it. These fields travel perpendicular to each other and to the direction of motion of photon. You see that here there are two fields in the motion of this light. One is from upward to downward direction and second one is from left to right direction. These fields are magnetic field and the electric field. In the ordinary light, the light travels in all directions. This is the movement of a light wave, and from this it is shown that it is moving in all directions. But for chemical analysis we use plane polarized light. The plane polarized light is generated by passing these non-directional light through a polarizer, which permits only one direction waves, and hence polarized light is created. This can be further explained by a simple animation. you see that light is emerging through this source in all direction. When a polarizer is placed in their path, it permits only a single direction light through it. And when this single direction or polarized light is passed through a sample of any substance, especially the chiral substance, it rotates this plane polarized up to a certain degree. For example, we have named this alpha degree in this animation. This is for the sample A in the sample tube, and when the same light is passed through the sample B, which is the optical isomer of the A, it rotates the light in negative alpha direction. It means that both the compounds are different from each other because both are rotating the light in the different way. This shows that both of the molecules have different optical properties. Hence, there is some difference between them. Actually, the interaction of light with the sample results in a net rotation of plane of polarization. The value of net rotation may be determined by viewing the emerging light through analyzer and rotating it until the light intensity reaches a maximum. To understand this, think that molecule has an atomic framework embedded in a cloud of electrons. Then you will recognize that the movement of those electrons over that framework generates an electric field, or simply, every molecule has an electric field associated with it. When you shine light on that molecule, the light's electric field interacts with the electric field of the molecule in much the same way that the magnetic fields of two magnets interact with each other when they are brought close together. If the light is plane polarized, the interaction results in a rotation of plane of polarization. Individually, all molecules rotate plane of polarized light. The magnitude of the rotation depends upon the relative orientation of the light as it encounters the molecule. If the rotation of one molecule is the mirror image of the orientation of other, the rotation by the first molecule will be mirror image of the rotation of the second. The net rotation produced by a sample is the sum of rotations produced by the individual molecules. The whole process is described by the following diagram, in which a polarimeter is used as a polarizer. You see that here is a light source in which there is a non-polarized light is coming out. This non-polarized light is passed through a polarimeter which polarizes the light, and up on uh, passage of this light through the sample which is enclosed in this tube, we observe the degree of its rotation. The sample composed only of achiral molecules like water or hexane has no effect on the polarized light beam. as the net rotation produced by a sample, which is the sum of the rotations produced by the individual molecule, is being cancelled by each other. However, if a single isomer, optical isomer, is examined, all sample molecules being right-handed or left-handed, the plane of polarization is rotated in either a clockwise direction or counterclockwise direction. The observed rotation of the isomer are always opposite in direction. One enantiomer will rotate polarized light in a clockwise direction, which is also called dextrorotatory and is represented by positive sign, and its mirror image partner in a counterclockwise manner and termed as levorotatory, designated by the symbol negative in small bracket. The prefixes dextro and levo comes from the Latin dexter, which means right, and levus, which means for left, and are abbreviated as D and L. Remember that both the signs are in small alphabet. If equal quantities of each enantiomer or the optical isomer are examined using the same sample cell, then the magnitude of the rotations will be same, with one being positive and the other negative. To be absolutely certain whether an observed rotation is positive or negative, it is often necessary to make a second measurement using a different amount of concentration of the sample. In the above illustration, for example, might be minus 90 degree or plus 270 degree rather than 90 degree. If the sample concentration is reduced by 10%, then the positive rotation would change to plus 81 degree or plus 243 degree, while the negative rotation would change to minus 81 degree, and the correct would be identified unambiguously. Since it is not always possible to obtain or use samples of exactly the same size, the observed rotation is usually corrected to compensate for variations in sample quantity and cell length. This is common practice to convert the observed rotation A to a specific rotation A under parenthesis by the following formula. The specific rotation, which is alpha D, is equal to the alpha divided by 1 into C, where divided by L into C, where L is the cell length in decimeter, C is the concentration of the sample in gram per milliliter, and D is the 589 nanometer light from a sodium lamp, which is usually used for illuminating or the light source. These specific rotations are useful in the way that they are determined experimentally and they are used to characterize and identify pure enantiomers. For example, caraway from caraway seeds have the optical rotation plus 62.5 degree, and this isomers may be referred as plus caraway or D-caraway, while the caraway extracted from the spearmint have the optical rotation minus 62.5 degree, and this is referred to as negative carbon or L-carbon. Similarly, lactic acid from the muscle tissue has the specific rotation plus 2.5 degree, and this isomer is referred as plus lactic acid or D-lactic acid, while the lactic acid which is extracted from the sour milk has the specific rotation of specific optical rotation minus 2.5 degree, and this is referred to as negative lactic acid or L-lactic acid. A mixture that contains the 50 is to 50, which means equal in quantity of the both enantiomers or the optical isomers, has no observable optical activity. Such isomers are called racemates or racemic mixtures. When chiral compounds are created from achiral compounds, the products are racemic unless a single enantiomer of a chiral co-reactant or catalyst is involved in the reaction. Chiral organic compounds isolated from living organisms are usually active optically, indicating that one of the enantiomers predominates, and especially in most of the cases it is the only isomer present. This is a result of action of chiral catalysts, the enzymes that reflect the inherently chiral nature of the life itself. Chiral synthetic compounds, on the other hand, are commonly racemates. Remember, the racemate is a substance which contains equal amount of both optical isomers. So net effect is 0. So the synthetic compounds are mostly racemates unless they have been prepared for enantiomerically pure starting materials. There are two ways in which the condition of a chiral substance may be changed. A racemate may be separated into its components in enantiomers, and the process is called resolution. And secondly, a pure enantiomer may be transformed into its racemate, and this process is called racemization. Now come to our main topic, which is the optical isomers. And now we will understand uh, or try to understand the topic using different examples. Here, for example, we have an example of R2-chlorobutane and S2-chlorobutane. Chlorobutane, both are the same compounds. One of them is called R and second one is called S. This R and S are the part of their nomenclature system that we will study in detail in coming lectures, but in a simple way to understand the topic completely, remember that the R is derived from the Greek word rectus, which means right, and S from sinister, which means left. Actually, we use the direction to represent from the lowest to highest priority groups. If it is moving in anti-clockwise direction, the compound is called S. And if it is moving in clockwise direction, the compound is called or designated with the symbol R. From right and S from left. Now focus on 2-chlorobutane. We have two-dimensional structure of the compound as well as three-dimensional structure of the compounds by this MDL model. You see that both of these compounds are mirror image of each other. That is, if both of these are placed in one of the compound is placed in front of the mirror, its image in the mirror will be created like the second one. Just like the mirror image of a hand of left hand is shown in mirror as right hand. Although both of the hands are non-superimposable and they are different from each other, and you have noticed that a glove made for left hand is not wearable on the right hand. Such molecules are called chiral molecules. So both these 2-chlorobutane, either R or S, they are non-superimposable. You see that they are mirror image of each other, and no matter you turn the compound, I am turning the compound to blue to keep the blue at right side like in this case, but you notice that the red color chlorine, in this case it is in direction coming out of the screen, and it in the second compound the chlorine is going behind the screen, or same is the case with hydrogen. So it means that both are non-superimposable and are mirror image of each other. In this compound, this carbon, which is gray in color shown here, is a center called a chiral center, which bears all the groups different. For example, here you see that the methyl group, this is the ethyl group at one side, at one end it bears hydrogen, and at the fourth side it has chlorine. So all four groups are different, which are attached to this carbon atom, and this carbon is called a chiral carbon. Chiral carbon. Such compounds in which a chiral center is present and both the isomers are mirror image to each other, they bear optical characters, optical activity. So they rotate the plane of polarized light in different directions. The optical isomers may be of two different types, that is, the diastereomers or the enantiomers. The enantiomers have only one uh, chiral centers, while the diastereomers have more than one chiral centers. It means that enantiomers are uh, mirror image of each other like this one, while diastereomers may not be the mirror image of each other. For example, in this case of 2-bromo 3-chlorobutane, which is an example of diastereomers, you notice that there are two chiral carbon atoms present in this compound. One of them is this one and second one is this one. And you notice that its uh, optical isomer is not the mirror image of this one, although the upper part of the molecule is the mirror image of this uh, molecule, but in the case of lower part, this is not the mirror image of the compound. You see that the green colored chlorine is at opposite side to this one, so it inhibits its optical or mirror image creation. We will discuss the enantiomers and diastereomers in our later section, as this uh, movie is only to make you able to understand what is the optical isomers. We will see our coming lecture in the near future. Thank you.